Welcome to The Explainer. Today, we're pulling back the curtain on the world of industrial manufacturing to look at this secret sauce, the hidden engineering that turns basic raw materials into the products we use every single day, everything from our food to our fuel. It sounds like a riddle, right? But the answer reveals this really clever shared secret, a set of engineering tricks that allow these huge industrial plants to run with almost zero waste. Let's dive in and see how they pull it off. All right, so to get these tricks, we first got to understand a huge problem that every single chemical engineer has to solve. Okay, let's say you're trying to turn substance A into substance B inside this big machine called a reactor. Now, in a perfect world, all of your A would just magically become B. But reality is messy. Chemical reactions almost never go all the way, leaving you with a mix of your final product and a whole lot of unused leftovers. So check this out. You might put 100 kilograms of your starting material into the process only to get 40 kilograms of what you actually want on the other side. That means a staggering 60% of your expensive raw materials are just sitting there, unused. That's not just inefficient, it's incredibly wasteful. So the million-dollar question becomes, what do you do with all those leftovers?
Well, here's the first brilliant idea. You don't throw those leftovers away. No. Instead, you give them a second chance.
The solution is to build a loop. Engineers create something called a recycle stream. It's basically a smart sorting system that catches the unused ingredients, separates them from the finished product, and sends them right back to the beginning to go through the reactor all over again. This one simple idea completely changes the game. And it gives us two different ways to think about efficiency. You've got single-pass conversion. That's how much you convert in just one trip through the reactor. But with a recycle loop, the number that really matters is overall conversion. That's how much of the fresh material you put into the entire system eventually becomes product. And with recycling, that number can get way closer to 100%. A perfect real-world example of this is making high-fructose corn syrup. Yeah, that stuff. The process uses a special enzyme to convert glucose into the much sweeter fructose, which, as you know, is a key ingredient in tons of foods and drinks. So get this. On a single run through the reactor, only about 75% of the glucose converts to fructose. But by separating and recycling that leftover glucose, the process achieves a near-perfect 100% overall conversion. That means every single bit of fresh glucose that enters the plant is eventually turned into the final product. We are talking basically zero waste. It's incredible. But you know how it is in engineering. You solve one problem, and, well, sometimes you create a brand new, hidden one. To see what I mean, let's look at the Haber-Bosch process. This is how we make ammonia for fertilizer, and this single process is credited with feeding billions of people. It's easily one of the most important industrial reactions on the entire planet. The nitrogen used in this process comes right from the air we breathe. But air also has about 1% argon in it. Now, argon is an inert gas, which is a fancy way of saying it's lazy. It doesn't participate in the reaction, it just kind of tags along for the ride. So what happens to this lazy argon? A tiny amount comes in with the fresh nitrogen. It goes through the reactor, does nothing. Then it hits the separation stage. Well, it's not the products, so guess what? It gets sent into the recycle loop along with the other unused stuff. And here's the trap. It has no way to get out. It just keeps circling around, and with every single loop, more fresh argon from the input joins the party. This is where it gets really bad. This accumulation causes the concentration of argon inside the system to just skyrocket. It goes from less than 1% to over 15%. At that level, it's like a traffic jam. It physically gets in the way of the actual reaction, poisoning the process and grinding the entire multi-million-dollar plant to a dead stop. So how do you solve the very problem that your first solution created? Well, with another surprisingly simple yet totally brilliant trick. They introduce an escape route. By intentionally bleeding off a small fraction of the recycle loop, they create what's called a purge stream. Now, this purge stream is a calculated trade-off. It's a smart move. Because yes, you do lose a small amount of the valuable materials you wanted to recycle. But, and this is the whole point, in exchange, you give those built-up impurities an escape route, saving the entire process from shutting down. It's a small, controlled loss that guarantees the massive gain of a stable, continuous operation. Okay, now for our final stream. This one isn't about fixing problems of efficiency or purity. This is all about giving engineers precise control over the final product. It's called a bypass stream, and it's pretty much what it sounds like, a planned shortcut. It allows a portion of the incoming material to skip a step, like the main reactor, and then rejoin the flow further down the line. So why would you ever do that? It's all about fine-tuning the final output. If a reaction is creating way too much heat, you can bypass some of the cool, fresh material to bring the temperature down. If you need your final product to have a very specific concentration, you can use a bypass stream to blend the processed stuff with the unprocessed stuff to hit that exact target. It's kind of like a barista adding a splash of hot water to a scalding hot espresso shot to get it to the perfect drinking temperature. Same idea. So if you take a step back, what you have here is this elegant engineering toolkit. The recycle stream maximizes your efficiency. The purge stream makes sure everything stays pure. And the bypass stream gives you precise fingertip control. And this is not just theory. This is the invisible logic that underpins our modern world, running at a massive scale, every single day, quietly making the products we all depend on. Uncovering this hidden logic, it really makes you wonder, doesn't it? What other complex, elegant systems are just humming along beneath the surface of our daily lives, just waiting to be understood? It's something to think about. That's all for this edition of The Explainer. Thanks so much for joining us.